Whoop. Of course. Where's my face cam? Oh, it's not plugged in. Whoops. Classic. Look at this fool. This fool being me. There I am. Hey guys, how's it going? Welcome to another episode of Ferris Makes Hardware. This is episode 15, which is called Gloat. And I'm not gloating because I had like a lot of progress or anything. It's not one of my streams without technical difficulties at the beginning, is it? Anyway, this stream is called Gloat because that's the name of a small, I guess, sub-project I might call it right now. That I'm working on for the xenowing. Let me pull it up on GitHub here. There's no README or anything, so I don't really need to pull it up, but anyway. So I've been wanting to start on, there's a lot of things to do on the xenowing right now. I need to work on getting HDMI working and bringing up the system on the new board and stuff. That's all fine and good, but one of the things that I've also been wanting to attack from kind of the other angle, so one of them is kind of bringing up stuff on the hardware, and the other one's kind of designing down the stuff that we're going to make in the hardware. Particularly what I'm thinking of is the rasterizer that I eventually want to do. And initially I was thinking that I was going to do the rasterizer on the system itself and then kind of iterate on it there. But the more I thought about it, and especially the more I thought of like the whole 3D pipeline, the more I realized how important the transform and lighting is as well. And so I think I kind of need to design both of those a bit together. And in order to do that, I need some test content either way, right? And I could either spend some time authoring that, or I could try to use some existing stuff. And it turns out the latter is what I'm kind of experimenting with doing right now. In particular, I want to have the whole sort of 3D hardware setup modeled in software as a software renderer. And like I said, I've been thinking about doing that for a long time, but instead of doing it on the system itself, I'm just going to do that on the PC. And in particular, I've been thinking like, well, what are kind of the average features that I want? And I want it to be more like PlayStation 1 style with no texture filtering or perspective correction and no Z buffering or anything. But when I was looking into ways of getting test content, there's a fair amount of open source models out there that are all kind of available. I forgot to link this in the chat. But getting all that stuff, even like a basic 3D test program actually has a lot of setup in terms of actually building it. And so what I kind of wondered instead is, why don't I look at some old demos and find ones that use some old fixed function pipelines, so early GL or early DirectX, or Direct 3D rather, because early DirectX is a bit before that, but and just see what kind of features of OpenGL or DirectX are they using, because I know in my experience from making demos especially, we don't tend to use that many features in the hardware actually, or in the API, because you implement like the handful of ones that your artists want, and then they bend those to the extreme, and that's kind of what happens. So in particular, I wanted to look at some old demo scene demos to see if I could use those as test content. And in addition, I also wanted to look at some like benchmarking applications and stuff. The issue with benchmarking applications is I think they would cover a larger surface of the API, which is kind of not the point. Like, basically, I was thinking that if we wanted to get one of these old demos to run, what I could do is I could implement that subset of OpenGL or DirectX. And in particular, I did end up choosing OpenGL, and that's what this is, which I'll get to in a second. But I was thinking that if I wanted to implement that, I don't want to implement like the full API, but I don't think I would have to. And it turns out that's kind of why I've been thinking about this like as an experiment, because I don't know if this is a good idea to do, but it turns out at least with the demo that I chose to start this with, this actually went really well so far. Like, I started on Saturday and I had vertex transformation done on Monday. And then I ended up fixing a couple bugs in the last couple days, and now it's pretty good. When demos that use glide be a better target? I think that'd be probably a more accurate target for kind of the era of hardware that I was picking, but maybe I should go back and do that. But anyway, early GL seems to be what I landed on. And I've seemed to be pretty happy about that. The downside, of course, is that a lot of these older demos use a lot of blending and a lot of they'll have Z buffering. And like I could make my renderer not have texture filtering if I wanted to do that and some other things, but it doesn't really matter too much. Because I'm thinking that it wouldn't be that bad to implement a rasterizer with Z buffering and everything. I mean, we have tons of memory. It's just more about scheduling the different loads and stores and all the things we have to do to make that work. But that might be kind of fun. But anyway, I got kind of far with at least getting one demo to work. So the demo I chose to start with, I went through a couple, and the one I landed on was Mosaic by Howjob. This is a demo from 2001. And as you can see in this project, it's actually in the source tree because nobody cares if I do that with the demo, which is kind of the other advantage here, is that I don't worry about like infringing on anyone's IP if I include the demo and kind of bend it to my will. So this demo, despite the pretty bleak amount of comments here, considering its age, I've always liked this one, probably because of the music. I think I probably saw this the first time in 2005 or something. It's a bit later than this, but I don't know. I've always kind of liked it, but it's also very basic in terms of like, it's mostly static 3D scenes, static meshes that kind of move around a bit or scale a bit. So it's just sort of transformations on static meshes. Again, a lot of blending. And actually blending is one of the things that I was hoping not to do, but as soon as I realized, oh, a lot of these textures are text, and if you want to have any text, you kind of need blending, unless you're going to do all that in software. So actually, I think I'm not going to get away from supporting blending. And then if you have the Z buffering, that of course really simplifies a lot of like the transform and lighting, because then you don't have to sort polygons, which never works out anyway because there's no really good way to do that. So I'll probably end up with a pipeline similar to this anyway. Now, so I didn't really know which kind of version of GL this would be. It turns out it's about version 1.2.1. Yeah, I could do it with alpha test. That's true. Could just do discard. But yeah, I think I'll end up doing... Well, I actually don't know if I'll end up doing blending and Z buffering and stuff, but I've been having so much fun getting this to work in software that I'll probably just continue that, and then that'll end up being the renderer because that's what I'll end up having. But anyway, so then I thought, well, how can I make this work? If I have this demo, of course it just runs on my PC. In fact, I can pull that up. I don't want to watch the whole thing. But you download it, get the executable and everything, and I can, whoops, actually need to delete this. If I just run this, of course, this thing still works. Let me turn my audio on. So again, basic geometry, a lot of textured quads, and a lot of blending. And that's basically what this demo is, right? Oh, that's cool, Danny Collin. I didn't know that it supported that little. I guess it's similar to the layer blending on the SNES. Of course, that makes it really simple because you just do an add and you drop the lower bit. Anyway, yeah, so just running that, of course, how does this hook up to OpenGL and everything? Well, it's just via DLL. So if you open this up in Depends, classic tool, dependency walker it's actually called, but I've always just called it Depends. This is Mosaic itself, and you can see all the different DLLs that it relies on. Most of these we just don't care about because what I was thinking to do is just replace a couple of these DLLs. In particular, if I replace OpenGL32, then we should be able to hook into all of the calls it makes to the graphics API and just implement those ourselves against the software frame buffer. So if we click on OpenGL here, we see all the lists of functions that imports. This list down here is all the functions that are available, and then these highlighted ones are the ones that are actually imported by the executable, and the ones up top are the ones that are just a shortened list of this. So you just see all the ones that are imported, and most of these are really basic: geobegin, gln, geoclear, call lists. So display lists. This was a feature that I actually didn't know about in earlier GL because I learned OpenGL in the OpenGL 2 and OpenGL 3 days, somewhere around there. And I think display lists were still a thing then, but I just totally missed them. My teenage self didn't, just missed them. And what display lists are is you can have a list active, so you sort of, just like you would with GL begin and GL end, and you list a bunch of vertices. You make it, I think you call GL new list, and then all of the, well, not all of them, but all the commands that modify server state in OpenGL will actually sort of be memoized. So they won't necessarily execute directly. There's a mode where you can have it do that, but it essentially collects all of those commands, and then you can end the list, and then later you can call the list, and it will have the effect of calling all those commands that you called between the new list and everything. Yeah, Liquid Wen. Oh, that's funny. Someone else brought this demo up too, and I actually might just try this today just to see if it runs, but I don't know if it will because it has shaders. Or at least the version of GL it uses, because it says GeForce 3 in the README. I checked it today, and that has some basic shaders, which actually this probably doesn't use. I don't know. We'll see. It might just work, which would be fun. Anyway, the call list would allow you to sort of batch all these calls, and especially if you're doing something like specifying a bunch of vertices, which GL at these earlier stages didn't have ways that you could specify like a vertex list and a normal list. It actually does have functions called vertex pointer and normal pointer, and then you specify a bunch of indices into those lists, and it kind of collects them in a slower way. So you didn't have like vertex arrays or buffers that you could do properly. So this was kind of necessary to get better performance if you're going to draw the same things over and over again. So sometimes faster, sometimes not. I'm not surprised about that, because I'd imagine, especially if you have like some indexed mesh, it probably ends up collecting and copying a lot of data. Who knows? But something to support. That was kind of the only gotcha when I was looking at this list, because you have like bind texture, blend func, and these are mostly just state changes. And then there's a lot of things about lighting and materials, but I mean, when you look at this and you're thinking, well, I really just need this as a front end to a rasterizer. I don't need to implement all these. I don't need to support all these features. I just need to support enough that the demo runs. At least that was what I was thinking in the experiment. Turns out I'm absolutely correct. Now this list actually doesn't tell quite the whole story, because you can see here we import GLU32, and that has a dependency on OpenGL also. But here we can see all the functions that GLU will also import. So what the reason why this is meaningful is if we go in here and we put our own OpenGL32 here next to this executable, then this executable will load our DLL. But also when GLU32 tries to link OpenGL, that also will link to our custom OpenGL. So we need to we need to support these as well. But again, we don't necessarily need to support all these, because GLU has a lot of features, and the engine, maybe it never uses GLU sphere or whatever it was called, and then we probably don't need any of these eval functions, for example, and that seems to be the case with this demo, that a lot of these just go unused. So we have to export those symbols, but we don't actually have to implement them. So yeah, long story short, and to answer Cetra's question, what I'm building is an experiment that I think is going pretty well. I'm building a custom OpenGL implementation for earlier versions of OpenGL, so that I can use like late 90s, early 2000s demo scene demos as test content for a software renderer that will become the model, like the software model for the hardware I'm going to implement for my FPGA console. And it might even be that we end up supporting like an early OpenGL version on the console itself, just because that ends up being the easiest thing to do. I don't know about that, but we'll see. Yeah, I could imagine that too, Daniel Collin. That's very driver and vendor dependent, that someone will essentially just do exactly what you would have done, or some would do some more smarter compaction or something. Who knows? I can definitely tell you what my implementation is doing, and it's doing the dumbest thing possible, but that's because we have a lot more horsepower here, and we can do the dumb thing, and that makes the implementation really easy, which is kind of the point. So that's the other thing. This little implementation started as just being, what does it take to get this demo to run, and is it enough that we can just do it? So I started that on Saturday, and it turns out that's not that much at all. So again, these lists are not that big, and assuming we wouldn't actually have to implement all of them, that didn't seem to be that daunting. Display list was the only thing that gave me sort of, that I had to think about up front, because I didn't want to like redesign around that later. But again, because we got the whole function list from depends, I could kind of assess up front what that would take. So anyway, just to jump into the code here a little bit. So I should actually run this before, just so you guys see where I'm at. So I have this little script that's just build and test. And what this is going to do is it's going to build my little Rust crate here. So I've done this in Rust. And I build a dynamic library, and I just call it OpenGL32. And then this build and test will just copy that to the Mosaic directory and then go there and run the demo. That's all it does. And I'm not even building it in release, and it's fine. So if I run this, and by the way, I'm using mini-FB, I should say. What happens is that instead of running with the regular demo, we can see this prints out DLL main process attach, and that's because it loaded our DLL. And it makes this mini-FB window, which just says gloat what up. And when I run this, it gives me the little Windows error message ding sound for some reason. I don't know why it does that. I just realized you guys aren't getting audio. Guess it's not terribly important, but it's nice music, so there you go. Anyway. So of course, because we hooked all the DLL functions, nothing's being rendered with actual OpenGL. But instead, I've implemented a lot of, at least the most basic parts of a transform and lighting pipeline. So here we have all the vertices being plotted, with the color being the normal of those vertices. And if you've seen this demo, this is going to be fun. I'm actually going to let this play because I enjoy watching this. But I'll show you a couple funny things actually. One of the things is that of course the content's kind of offset here, and that's because this window is actually a slightly different size. And of course the demo makes perspective matrix and everything such that it fits the actual window, but we're not drawing to the actual window, and I don't do anything to get the actual size of the window. I think I can do that with the device context, and I'll get to some more of that later. But what's funny about it is that if I resize this window, then the content changes. Because again, it calculates the perspective matrices and everything to this window, even though we're drawing to this one. So that's kind of funny. Another funny thing that you notice is that in all these, there's a lot of parts in this demo where it just is like a static picture. And in all those parts, there seems to be a cube in the middle of the screen that's just hanging out, probably behind the 2D content. So that's kind of funny. Maybe it's some test scene that they put in there just to show the 2D content. Who knows? I think this is really cool. And again, what I found and what I was pleasantly surprised about, but also what I was hoping for. I think this scene runs a little slow, but other than that, it's fine. Again, it might just be because I'm using a debug build this DLL, but we'll see. Anyway, what I was surprised to find out about, but also what I was hoping for, is that the API service that I had to implement actually wasn't that bad. And there's a lot that I still haven't implemented. In fact, all the stuff you see printed out here that's just because it prints out a function name and its parameters for the functions I haven't implemented. Like I've exported symbols for them, and they call functions, and then they usually will dispatch like a command, which I'll get to what that means. And then this just says, okay, well, we would normally execute that command, but I haven't implemented it, so it prints it out instead. That's all it means. The demo's basically done at this point. It's showing a bunch of 2D content that, of course, I don't show here. But anyway, it works. If I hit escape, then then that's it. You can see these threads detached and everything, because you get callbacks in Windows whenever threads are created or destructed or destroyed, I guess. And you get every DLL gets those callbacks. That's all that is. And then here, make current delete context, and DLL means this is when the DLL is unloaded, and then we're done. So yeah, so it's pretty cool. It's obviously really fun to make this because all I did is I started, I'll just make my DLL called OpenGL32 and then have it try to load. And if you do that, you get very quickly to just this loop. So like if I get rid of WGL make current, if I just don't export this and we try to build it, then of course what happens is when you run it, yeah, it just crashed. And if I run it again, it's because this procedure entry point, WGL make current, cannot be located. So you just add that, right? And you do that over and over again until all those are there. Yeah, that's a good point, Daniel Collin, that I actually hadn't considered. That's actually a really good point that I could use Verilator to hook up the rasterizer and just start replacing parts of the software. Yeah, that's a really good point. I hadn't considered that at all, actually. But that's definitely something I could do. I'd have to come up with like how many cycles, some kind of timing solution, but that's probably a good idea. But yeah, so I literally just did that until I had like all the functions enumerated. And as you can see, most of these, like WGL create context, is actually never called by this demo, which is bad. Don't do that, you guys. Don't use OpenGL and never call this and just assume there's going to be a rendering context. I don't know what the hell's going on with that, but anyway, all these ones that I didn't implement, I just exported them and then added unimplemented. So that's kind of funny because one of the things with this approach too is like, I don't need this to be a good OpenGL implementation. I don't need this to detect errors. So I can just have it panic whenever anything goes wrong. And that's totally fine. Yeah, I think that's doable too. I think that's a really good idea. But yeah, this is stupid. It does call make current and then delete context on a context at the end, which is kind of funny. But before that, I don't think it calls make current. It doesn't create the context either. It just assumes it's there. We have viewport, and we could use that for determining the window size. But so that's another thing, is that in Windows, this is all actually pretty separate, like the windowing system and then the graphics API. And first of all, you don't want to use viewport to determine the size of the window because there may be like picture-in-picture kind of effects, so the viewport might be used for something else, and I don't want to make that assumption. So right now I just hard-code the window size 640 by 480. We do actually get, like, because I think if this did actually create the context properly and then call make current on it, then we could at least get the device context and the rendering context. So we could, I think through the device context, we could get the window and find out the size. And then probably keep a list of like rendering contexts and their associated device contexts in case there were multiple too. I also don't do any threading here, by the way. So this is the dumbest implementation you could have, but it totally works. So that's good enough. Anyway, if we did that, then we could probably determine the window size there, but also it might change. So I'm probably going to do that in swap buffers, but also I don't really care because this runs enough. Anyway, my point is that we don't really ever get told what the window size is, so that's kind of something that we have to just assume or deal with. Another thing is that even though, since we replaced OpenGL32, of course that works for all these GL calls, but then there's a really important call that we don't get, and that's swap buffers. And so the reason why I have swap buffers here, so I did this kind of weird. So we want to know when the buffers are actually swapped, and we could like try to get clever and just like, oh, whenever there's a clear, we could display the latest stuff and then do the clear or something, but that's stupid. So instead what I do is, since MiniFB actually doesn't use swap buffers, what we can do is we can just hook swap buffers globally. So on DLL load, what we can do is so I'll have my DLL import swap buffers from GDI32, and then what I can do on DLL attach, I'll just show you this. When I make my context in particular, I have this thing here, which is this patched function. So here, I'll show you, where's my DLL attach? Or DLL main, right? So DLL main is just something that Windows calls whenever you attach to a process or detach. And whenever that happens, I just create a context object, which is this global thing, and that's fine. And when that's created, it creates this patched function object. Yeah, exactly, Daniel Cullen. But I can actually work around that. It's not a problem, but it's nice that I haven't had to yet. So don't hold back. But this patch function, what it does is it actually goes and overwrites the first instructions of the swap buffers function, and then inserts a jump into whatever my function is. So in this case, I have the original function address and then whatever I want it to be patched to. And so I create this patched function with the original one and then mine. And so then I just overwrite the first 5 bytes of the actual swap buffers in GDI with a jump to my own. And that totally works. And I mean, the thing is too, is that I also read out the original data. So like I could also restore this. So if I wanted my swap buffers, since my swap buffers, I think actually does already call minifb update. There's a swap buffers that I have for the calling convention. Then I have it dispatch onto the context object. And then here, we do update with buffer here. If I wanted to, I could also just say like undo the patch here and then redo it after we call update with buffer. So I think this is safe enough. Again, these are the kind of hacky things you can do when you don't really care. Like this is not by any means a GL implementation I would ever have anyone else use, but it's actually, I think, a pretty good way to do what I want, which is to get content through a rasterizer. So I'm pretty happy about it. But yeah, so that is one nasty thing that we have to do. In fact, I think that's the nastiest thing that this has to do. And that's in order to, again, get the swap buffers call, because otherwise we'll never know when that's supposed to happen. So good enough. And then the rest of it is just a really simple GL implementation, or I should definitely say subset, because again, I've only implemented stuff that I've actually encountered with this demo. So I did the same thing where it was just like, okay, after I would patch all the functions, then the thing would finally load, but then all the functions were unimplemented. And so I'd run it. So like, let's say we have this. Now if I run this, the demo will load and we'll get the dialog box and we hit run. And then very shortly after it crashes here, some runtime error. And that's because this thread unnamed panic is not yet implemented, and it gives me the line number. So then I can go in here. Oh, okay, that's GL call list. And then I'll like start to implement that. So pretty basic. And the whole like architecture here is really straightforward. Again, because it's trying to be as simple as possible. There's this context object, which represents everything. Basically a GL context, and we assume there's only one, which a normal implementation would not do, but that's fine for us. And yeah, I thought about that too, actually. Like at least to like extract some kind of display list that I could send to the actual hardware. To do that, though, I need a higher bandwidth connection to the hardware. So I don't know if I would need to set up the Ethernet stack or something else. I might still want to do that, but I don't think the USB UART is going to be fast enough for that. It might be, actually. Who knows? But that does actually sound kind of fun for testing. So maybe I'll end up doing that. Who knows? I probably won't, just knowing how lazy I am about setting that kind of stuff up. But I think that is a good idea, and that's definitely. Man, if I had a lot more time, I would do so much more of those kind of solutions, because it just makes more sense to kind of move things over more and more progressively like that. But I don't have as much time as I would like, so I probably won't do that. But I like that idea. Anyway, this context object just has all the state you'd expect. There's a clear color. There's a list of display lists. There's the model view and projection matrices. There's a matrix stack because you use push and pop. There's a matrix mode, which is like which matrix all the matrix functions will operate on. There's a list of textures. There's the texture 2D binding, primitive mode. So this is like if you do GeoBegin, then this becomes sum of triangles or quads. There's the current normal. There's this list of assembled verts, which I think I should actually call this issued vertices or something like that, because this is the vertices that it collects as you call GeoVertex in between begin and end calls. There's a bunch of state about packing and unpacking, and this has to do with reading in texture data. Now the demo actually does, in fact, I can show this pretty easily because I'll just quit the thing right away. Here you can see there's a ton of these text image 2D calls, and most of these, if you look at the sizes, they're decreasing powers of 2, so it's clearly generating a bunch of bitmaps, and I think it's actually GLU that's ending up calling this. And right now I'm not doing anything with that data, which is why this is printed out. So eventually I'll have to actually deal with this, but I did implement a lot of this state because there was a bunch of pixel store calls, which again I think comes from GLU they were changing these. So I thought, well, I'll just click those. Then you have the normal array, the vertex array, and then the viewport parameter. So it's again really basic. And then as you might imagine, most of these GL calls basically map to just changing some of the state. So it's really straightforward in that sense. The only thing that's kind of not straightforward is again the way that I supported display lists, but I did it the most straightforward way possible, and it totally works. And the way I do that is to have this enum, which is all the different commands that can change the server state. So this is literally just I take the raw parameters that you would have given to GL, except in a couple places I change it. So if you give it these ones that take pointers, I do data copies into the structure, and then that's it. So then if so I can show you a lot of these calls. For example, this one, multi-text chord 2FARB, this will call this issue. So it will build this command, which just takes all those parameters and puts them in a struct, and then calls context.issue. And then what issue does, and this is the only clever part of this whole thing, is, let's see, where is it? Let's do function issue. So what issue does is if we have a new list, so if we're between new list and end list or whatever it is, then we check the mode. If it's compile and execute, then we're going to execute the command. Otherwise, we just add it to whatever display list is our current one. And then if we don't have a display list current, then we just execute it right away. And that's it. And so then execute is where actually all the work ends up being done. So in execute, there's this, you give it a command reference, I think, and then it will just match on that and actually do all the state changes and everything. So it's that one level of indirection, and that gets us display list support, which is pretty good. And then all the stuff that just modifies only client state, then I just make as functions on the context itself. So gen list, gen textures, all these things that don't go into display lists. So again, other than that, it's as straightforward as you'd expect, which is pretty cool. And it does do a bunch of error checking, but mostly that's just to catch all the cases I haven't implemented yet. So the first thing I do when I see like it does text gen, I want to support that. What I'll do is I'll just say match on the chord, and if it's not one that I reckon, I'll match on the chord and then only have this default case where it panics, and then I'll run it, and then it will tell me the value of this, and then I'll go back and look at the specs and see which value that was and add support for just that, and then do the same thing with name and param. So it's somewhat tedious, but it's also like really mechanical, so it's kind of fun. You put on good music, and then it's the kind of task that you can do really effectively. Just by sort of chugging through it, and it's fun because the more of these you implement, the more the demo works, and I find that kind of task really fun. It's just like bootstrapping an emulator in kind of the early parts when things start working. But this was easier in a lot of ways because most of the system already works because it's just a Windows executable. So we're only sort of bootstrapping this display stuff, and also like you see very clear patterns in what the demo actually does very early on, even before things are implemented. So again, like it's quite obvious that it's uploading a bunch of bitmaps here. And before that, it's doing some text chords. So here, I think it's going to enable some blending and probably draw a texture to the screen or something. So it's kind of cool to see that working progressively. So that's again what this project is. Yeah, I guess RenderDoc's doing something similar, definitely. And that way it's able to actually capture all the data that goes through, not just the calls. which is a good way to do it. I mean, you see everything that the API sees, so pretty straightforward. And I thought that too, like maybe if I wanted to capture some of these lists, then I could actually do it that way. But who knows? I thought also that like when I start doing textures in order to debug texture upload and everything, that I could also have some very simple debug UI where I could view the various textures that are uploaded. I should also say one of the things that also makes this really simple is that this demo never deallocates anything. And that makes it easier because then we can just use like increasing indices for a lot of the stuff that's allocated dynamically. And I just don't have to care if any of this stuff gets freed. As soon as I run a demo that does do some of that stuff, then I'll have to change that. But I may never run a different demo with this, actually, is kind of the other thing where, I mean, if this demo works, it has a lot of the features that I want. So I may never run another GL program through this, but I probably will for fun because it's kind of motivating. I think one of the things that might not actually be technically correct is when you have these GL array element calls, this is where you bind a pointer to some vertex data and a pointer to some normal data, and then instead of calling GL vertex, you call GL array element, and you just give it an index, and then the GL API is then expected to go and via the pointers you gave it, it will go actually read out that vertex. And again, just to make this normative with everything else, I issue those as commands. So sort of internally, it's as if you called GL normal 3f and GL vertex 3f, which I don't know if it's exactly semantically correct that that's how it happens, but that's the easiest way to implement this. And again, we don't need to be conformant, or we don't need to be actually conformant to the spec. We just need to make the demo run. So I think this is good enough. Hey, Dark Second. Oh yeah, MSys007. Sorry I didn't reply, but the answer is, I think what we're gonna do is actually do the rasterization part of this little GL implementation that I'm doing to test out a renderer. Because again, all this is just for, like, I want to do a rasterizer for the xenowing, and I need to do a software model for that where we can handle most of the details. And in order to test that, we need some test content. And a great way to do that is to try and leverage some existing content. And a great way to do that is implement a graphics API, or at least enough of a graphics API that is feature limited. So you're not spending all your time working on that, and supports some content that you like to look at. And also that seems to be representative of the kind of features you want. So again, the feature set here is a little bit more advanced than I wanted, but there's a lot of corners we can cut, and I still think it'll be good. And it might be fun to see this demo without multi-texturing, with not perspective correct textures, with no texture filtering, for example, as we're kind of bootstrapping this stuff. So I think that'll be cool. Anyway, so I got through most of that stuff, and then I added the normal processing. I realized I had made some mistakes in the matrix multiply code, and I ended up fixing that, which also uncovered some issues in our demo tool, which I'm really embarrassed about, and we won't talk about anymore. But that's going to be a big rabbit hole. And now the last thing I did, which I think I did yesterday, was I actually had it render the color of the normals, which you guys saw. And then the last thing I did is I also started to make it kind of more like actual primitive assembly. So what it does when you call like geovertex and everything, Daniel Collins laughing because he knows the feeling. What I do is I collect all the vertices when you call like geovertex a bunch of times, and then on end, this is where I actually do the processing. And most of this is just so I can kind of test this batch processing. Again, if we do any kind of hardware TNL solution, which maybe we'll do for the xenowing, I'm not sure. Then this is kind of how you'd want to do it. You want to batch up all the work and then have this sort of happen in bulk. And also this just puts it all in one place. So instead of like all these transformations happening immediately, they can all just happen in bulk. So we make sure first that we got the right amount of vertices issued, and then here we do all the transformations. So this just goes through all these and then gets these positions, and then we go all the way to normalized device coordinates here and just overwrite the positions in this case. This might not be correct, but this is what I have now. And then we go through and actually do these. So here we assemble these, and I've called this function assemble triangle. So here the demo uses triangles and quads. And then I call these assembled triangles with the actual vertices. And I end up copying the vertices, which is kind of crap, but good enough for a model for now, so that's fine. And I call this assembled triangle because this is like before clipping. I was thinking that this was going to separate itself into two functions, where this one is where all the clipping is going to happen, because here you want to issue sort of two triangles that make up this quad versus this triangle. So it's kind of this hierarchical idea where both of those two triangles shut up, Siri. That's funny. Where both of these triangles might actually be clipped after this stage. So yes, that's why I have this assembled triangle, and then this will do the actual clipping and then call rasterized triangle on the individual triangles after that. Yeah, clipping is a pain in the ass. That's not something I want to do yet, so we're gonna ignore that for now. Although, actually, with the rasterizer implementation that I want to try, clipping might not be that big of a deal. And let me pull this up. So I did a bunch of research a couple months ago about what kinds of rasterizers that I could implement, and so I ended up with this paper. Yeah, it totally is the worst part of the clipping and making the renderer watertight. Those are the worst parts. I think clipping's worse because it's subject to like precision issues in a way that the making things watertight actually isn't. Anyway, I ended up on this paper. This is, if you guys want, this is by Juan Pineda, parallel algorithm for polygon rasterization. This is from '88. This is not a novel idea. And I've found this paper through a couple different avenues. A lot of people that have tutorials nowadays on how you do renderers, they reference this kind of rasterization because it's fairly close to what a lot of modern hardware does. I mean, modern hardware is a lot more advanced than this, but some of these ideas still apply. And also, this is what the Voodoo cards used. At least the Voodoo 1 definitely uses something that's based on this idea. So it seemed like a good idea. And the other thing is that it's, in particular, this algorithm is really parallelizable, and it should make for really simple hardware because you calculate some setup stuff, which we could do all in software, which is actually what the initial Voodoo cards do. Is the Glide implementation actually does a lot of the like clipping and TNL and everything in software, and then the rasterizer itself is the only part that's accelerated. And if you set up all the parameters, then the rasterizer mostly just becomes this kind of walking machinery, and it kind of walks through this sort of bounding box of the triangle and just does adds for every pixel, either adds or subtractions depending on which way it's walking. And if you set up all the parameters right, you can do all this in fixed point such that your operations for every pixel is you just kind of do an add to move over, and then you do a couple sign checks, and then that determines if you're going to render or not, and then you have all the parameters there. So you end up with a lot of registers that are kind of all your interpolators. You have the normal ones you'd expect, which is like the let's see, it had it in here somewhere. Yeah, like red, green, blue, Z, and then you also have these edge functions. And these edge functions would act the same way, but they have this property that for every edge, you have it's positive on one side and negative on the other. And the idea is that it's a linear function in both x and y. So the idea is that you interpolate that across the triangle just like you would with all your other parameters. And when the signs for all of these are positive, that means the sign for this edge and this edge and this edge are positive for a given pixel. That means that pixel is inside the triangle. It gets slightly more complicated when you determine if you're inside or outside, because you want to not have overdraw with another polygon that shares the same edge. But then there's like the top left rule that's pretty standard for dealing with that. And that also fits into this relatively well. But we're not going to deal with that today. I'm hoping that we can actually get to something that might draw some of these polygons. At least we'll start with just the mounting boxes of the polygons, and then we'll go from there. But it seems to be pretty good. It's because you have all these values interpolated. This would amount to fairly high register pressure on a modern machine. Probably not, because you could put all this in SIMD, but you're doing a bunch of conditionals, so it might not be a great idea to do that anyway. But Again, this just needs to be a model for the hardware we're going to make, so we don't need it to be particularly efficient on my PC here. And again, the other advantage of using these older demos is not only do they not use that many features, but like the poly count and everything is naturally kept pretty low. So I don't think performance on my PC is going to be a big issue anyway. We'll see how wrong I am once this actually works. But yeah, but again, each one of these would just be like a 32-bit register, and then you have a ton of parallel adds in the actual hardware, which is really easy to describe. So shouldn't be too bad. And what I'm going to do too is I'm going to take a lot of liberties here. So what I'm going to do is I'm going to do all this in floating point first in the software model, because we're just going to get it to work. And I think that it should all work out mostly such that, as it mentions here in the paper, that the fixed point one basically works almost identically, except that you can do all of your transformations in floating point, and then at the very end, when you prepare them to like the initial values for these interpolators, then you just round them and then it should more or less just work. So we'll see. There's probably going to be issues with rounding and making sure that our all of our coordinates agree with that rounding. So if we round the like X and Y positions, then we might need to adjust the U's and V's and everything, but we'll cross that bridge when we come to it. And again, that's why we're doing a software model, because then we can fix all those kind of bugs in a software renderer and not have to worry about them in the hardware implementation. Oh, that's cool. Yeah, I'm totally just going to do it in floats first. But when we move to the hardware, I'm going to do it as integers, because then I don't have to implement floating point hardware. Otherwise, I'd probably keep it floats to make it easy, because there aren't that many parameters here that we have to do. So should be okay. So I actually thought that the first step to this, I've been talking a lot already, but that's just to get a lot of the background information here. First of all, I should actually say I love that I chose this approach, because I've been having so much fun with it. So even if I end up with a very different rasterizer than the one I wanted, or a very different one than what we end up in the console, this has been a really fun project just to do this. So I'm happy about that anyway. So I also wanted to share that, but also I think we're going to start with Shader Toy, because, you know, maybe it doesn't make sense to start with Shader Toy actually. I was thinking to kind of work out some of the like edge functions and everything in a shader first, but it might actually just make sense to just do it in the real deal, because it's not that bad. Oh, Shader Toy is so slow. So I'll zoom in a little bit. But yeah, we can just start with having some coordinates move around by like sign or something. We'll start with that. So actually, it's just easier to think in this kind of way. And the other thing about this algorithm is it lends itself very naturally to this kind of approach, because all of these functions, the idea is that you can evaluate these edge functions and all of your interpolators and everything sort of anywhere within this area. So like if you specified for a starting vertex what the values for like U and V are going to be, and then you have the deltas for U and V in screen space, then you can move around this triangle any way you want. And by sort of the same extension that we can kind of calculate what those are going to be sort of the other way, where we have the pixel position initially and then do it that way. So this should lend itself naturally to working in a shader. I don't know if I explained that very well, but I don't really care. Hey, Alkama. So let's do this. Let's go ahead and, well, this UV is fine. I don't need the color except eye time. I always forget that. So let's do this. Vec2 V0 is going to be some stuff. Yeah, I have Bonzomatic and what happened to my keyboard layout? I have Bonzomatic and our own tool, but this is just easier. And I'm not signed in. Maybe I'll fix that later. Hey, Petros. Yeah, it should be quite good. If we add like different pixel pipelines, it should also be really easy to just make that stuff work. That's kind of the other advantage of that approach, is that you can kind of walk the triangle any way you wanted once you have the both deltas and screen space for every value that you interpolate. So there's a lot of freedom here, which is nice. Okay, yeah. So let's go ahead and do some sine cosine stuff. And I think this, let's actually make this centered around 0 for fun. -1 to 1 is what we want, so we'll do times 2 minus 1. And then actually just doing this will work, which is nice. Nice to keep all this easy. Do I time cosine of I time times 0.8. Let's do some values here. And what I'm going to do first is this. So we'll draw a point. Let's see, vec3 point, vec2 uv. And here we can do return step length. With the UV, we also want the vec2 p. The length, actually we can just do this as a little SDF. Nice and easy. Length UP minus UV, and then we can bias this. And so then this becomes really easy because we can do like vec3 color is vec3 0. And then we can do frag color is vec4 color. And then here we can do color plus equals point UV v0. And that, why doesn't that work? Oh, do I need to do, is that step? I actually think it's the other way too in GLSL. So you actually do like that, don't you? And why isn't Control Enter working? That's annoying. Alt Enter? Yeah, that works. There's our point. And we can make this smaller. And things are pretty stretched here, so we might want to fix that aspect. In fact, I think the way we do that is to do frag chord minus I resolution dot xy over 2. And then we divide by just y, don't we? And then I don't think we do times 2 minus 1. Frag chord. Oh, cool. I should try that out. Okay, so we bias by this because we subtract the resolution divided by 2, which would subtract the midpoint of the screen. And then once we divide by y, I feel like this is correct. No, I think we need to multiply it by 2. Yeah, there we go. And now this square area in the middle is our -1 to 1. And that's fine. Just to document the range there. Good. Okay, so then the other nice thing about this, oh, by the way, this I think is inverted. Because I want this to be, is that what I want actually? No, I think that's still what I want, but I want 1 minus this. Okay, and again, we can do the size here. Okay, so now we have a vertex, and what I wanted to do with this is color it. So we can do vec3 red, so we can color code the points. That's the idea here. Okay, and then I need to actually generate the other points, which is the easy part. We just swap some sines and cosines, and we do some multiplies. Okay. Did I drop a thing there? Yeah. There we go. So now we have 3 points. And now we can actually evaluate some stuff. So let's see. What else do we want to visualize? We probably want to visualize the edges. So we want float line like this. Yeah, the tools are what matters, not the content. Distance to line 2D. Look at me Googling. Line defined by 2 points. This seems to be divided by length. Actually, isn't there a distance function? A, B, and GL? There totally is. Numerator is twice the area of the triangle with its vertices at the 3 points. X0, Y0, P1, and P2. I'm just gonna write this out long form because I just don't care. So this is P1, P2. This is the kind of math I just wish I had in my head, but we'll just do it the lazy way. I realized too, it's a segment that we want to, so we actually want to clip the ends. I should find a different shader that does this. That's what I should do. You know, let's just do it this way. B dot y minus a dot y. Let's say the one. A dot y minus b dot y times uv dot x plus b dot x minus a dot y times uv dot y plus a dot x times a dot y, no, times b dot y minus a dot x times, no, b dot x times a dot y. So this is the equation for a line. Yeah, that's a good point for Littleski. I should have reached for that sooner, shouldn't I? Yeah, we're going to steal that straight up. That's going to make our lives easier. Let's just do that. There's a reason why he writes it down, right? So then let's do something like this. And so in this case, we'll do, for example, v0 to v1. Oh yeah, we need the uv as well. Okay, and of course, this is the distance, which is not actually what we wanted. Because we're going to do a step function here as well. I think we want to do the same thing here. Good. And I'm actually going to make this one not as wide as the points. Even less if we want. Also, we can multiply these so they don't go all the way to the edge by doing that. Cool. And I don't care that the additive blending here ends up kind of sucking a bit. That doesn't really matter to me. So we can do 1 to 2 and 2 to 0. Then we have a triangle. Pretty. Okay, but this is just to make it easy to visualize. All right. So now we want to calculate, for example, our edge functions. And they should actually be really basic. Actually, the first thing, do we want to calculate the bounding box? Don't think we need to. I think really all I want to do is calculate these edge functions, which actually looks like it's really easy. It's this formula here. In fact, here's what I'm going to do. So we'll do float edge and vec2 v, vec2 a, vec2 b. And the edge function, I'm just going to copy it from the paper here. We're just going to do uv.x minus. Okay, we have a couple things because first we have x and y. So we'll do vec2 xy is a, and then we need dx and dy. The dxy is this. And that's just going to be b minus a, I think. So then we have uv.x minus x.x times dy. So minus uv.y minus xy.y. This is xy. Times, this was a bad notation. We'll call this d. So then we just have like dx and dy, which is better. And then we can call the xy p. So we have p and d, which I think is more natural. And then we need to calculate the edge functions. So what I want to do here is we'll do color plus equals edge, and that'll be uv v0 v1, right? And this actually gives us exactly what we want. As you can see here, where this value is 0 is right on the edge, and you can see it increases this way, and presumably it's decreasing this way, but below 0 because everything's clamped on the output. Now also you'll notice that the orientation of this actually matters. So in our case, I can pause this, which is quite helpful. Hey, two curves. Yeah, we're going to be working on a rasterizer that's going to be a model for the xenowing, but we're doing some testing in Shader Toy to test an approach. So yeah, the orientation here is kind of important. So actually, since this isn't clamped, I'm actually going to make this a step function as well. Like this. And there we should see quite clearly it's on that edge. So I'm going to do this too, times 0.2. So what's it, red, green, blue? So this is 0, 1, 2. So this is counterclockwise. And we can see here that the edge is positive when we're on sort of the, what's it called, the right side. And this actually matches exactly the paper. And then it's on 0 if it's on the edge, and then it's going to be negative if it's on the other side. So what we can do next is determine the ones for the other edges. And in fact, I'm probably going to steal these colors for this. Zero, 1, 1, 2, 2, 0. You know, I'm not sure we needed to do this in Shader Toy now that I'm looking at this, but I don't really mind that we did, because at least we get a good grasp on what this is going to look like as we debug this, which is going to be nice because we can iterate so fast. So now we can see these are sort of the different edge functions. And when they're all negative, in this case, that's when we're inside the triangle. And when they're all positive, we're going to be outside the triangle. That's kind of the idea here. Now, I think that's actually backwards to what they talk about in the paper. That probably has to do with orientation, actually, because here the y coordinate is flipped to how we would normally think about it in the rasterizer. Or it might just be a convention as well. So I don't think that really matters. It's just it's positive on one side, negative on the other, and as long as we decide one of those that we want, it becomes easy. Because in this case, what I can do is I can say inside is if all of these are less than or equal to 0. All these step functions here, all these edges. So I could do E01, gonna be this. And I'll just copy this here. I'll just do this again because it's so easy. 2 and 2, 0. So the 3 edges. And we can do it this way even, because this is what our rasterizer is actually going to do. So inside is going to be E01 is less than or equal to 0, and E12 is less than or equal to 0, and E20 is less than or equal to 0. And then if inside, then color plus equals vec3, some loud color. There we go. So there we see we have sort of visibility of the different edge functions across the triangle. And then when they're all less than or equal to 0, we're inside the triangle. Now, interestingly enough, why does it look like that when they're all backwards? Why does that change shade? That's a bit unexpected, right? Maybe it's not. Maybe, oh, I know why. This is actually kind of cool because I know what's going on here. So when all of our vertices are, in this case, let's wait for the right moment. When they're in sort of the correct order, the counterclockwise order, so red, green, blue, we can see that it gets a lot brighter. In fact, I'm gonna make that totally white so we can see that. And what's happening here is when they're in the counterclockwise order, we can see that this edge function is, they're all less than or equal to 0 when we're inside. But as soon as one of these vertices goes on the other side, then what we're actually seeing is that instead of all these being less than or equal to 0, they're all greater than 0 inside here. And what we're seeing here is the combination of these edge functions. I am quite certain of that. So if we comment out one of these, for example, that shade will change. And there you can even see it's because these two are both positive. We're on this side of this edge and we're on this side of this edge. Or this edge and this edge. So this also gives us backface culling, which is actually something we don't necessarily want, unless the demo actually says that that's what we want. So we want to be a bit careful about that. Hey, Michael C, Lord Takipo, Sai Attack, Yanamaran. Good to see you guys. Yeah, this is the game console. We're doing some prototyping of the rasterizer, at least playing around with some of the math. So the point of this is that this becomes really, really simple to express. So the simplest version of this, which is what I'm going to implement first, is more or less going to be an exact port of this code, where I'm going to, like, we have the actual vertices, and I'm going to actually calculate these edge functions, every pixel in floating point precision, and do all this logic to do the initial rasterizer. This is not what we're going to end up with in the hardware. This is a good sort of first step towards implementing this. So the paper actually talks about this, where if you take the bounding box of the rectangle, and that's what I'm going to do, or the triangle, I'm going to take the bounding box of the triangle and then do all of this for every pixel in there and then write out the pixel. And first I'm actually probably going to write the whole bounding box because that makes it even easier. But anyway, we need to evaluate, like you could traverse every pixel within that bounding box, or you could do some smarter traversal, which sort of reverses direction once you get to the edges, because this is going to be, we're only going to have a few pixel pipelines, so we're going to want to traverse the pixel. Because if you do traversal like this, like the bounding box, then even if you have the largest triangle possible, the best coverage you can get is 50% of the pixels. You get half of this covered by the triangle, and then the other half is going to be wasted computation. So this is actually a pretty bad way to traverse this. But the nice thing about this algorithm and what they're talking about here is that the traversal is kind of decoupled from the actual, from calculating everything else. And everything else just works out really nicely. Because instead of evaluating this at every point, what we're going to do is we're going to evaluate this at some initial point. And then we're just, since these are all linear functions, like these edge functions, and then all of the other kinds of interpolation we're going to be doing for the other parameters, we just need to sort of increment these values by dx and dy, like the pixel deltas, for every pixel. So we don't even have to evaluate this at every pixel. But the initial implementation is going to do that because that makes the most sense to me. So I think I'm ready to just try that. So I'm going to just pull this down here. I don't really care about publishing this test. I might save it for my own records and then I'll tweet it or something, but it's not terribly important. because it's all in the paper. So the first thing I want to do actually is what I'm doing here in this assemble triangle right now. It just goes through all the vertices, turns their normals into colors, and then it just draws each vertex. It plots it. So you're going to get a lot of redundant plots with what this is doing currently, but that's just a test. By the way, I need to BRB for a couple minutes, or not that long, but I need a drink. Okay, sorry about that. Something in my throat. I don't know what it is, but anyway. So what I want to do first is this. We have all the NDCs of the actual of the pixels themselves. I think we can also do this vertex transform when we do the vertex transformation. So I want to bake this into that next, and then I want to actually look into, instead of displaying the individual vertices like this, then we'll find the bounding box of the triangle and we'll render that next, I guess. That shouldn't be too bad. Now, one of the things too, with this other approach that I mentioned, of course, is that we do get sort of backface culling kind of for free, but actually we don't want to. That's not what we want to use for backface culling, because we would really like to not process any of the pixels if we know that the edge functions are going to be all negative, for example. So I'm not entirely sure what the best way to do that is. Probably just to actually calculate do it the normal way, where I think you do the cross product of some of these vertices and you take the sine of something. I don't remember what it is. I think it's the cross product of the edges and whether or not that's sine or two of the edges, and whether or not that's positive or negative, I think gives you the orientation of the triangle. But again, we're not going to worry about that yet. Just something that I'm thinking about. Yeah, exactly. 2 curves. Also need to be able to selectively enable and disable it, and also because we need to detect the face orientation, and then if culling is, so like if we detect that we're a front face, or a back face, and then front faces are supposed to be culled, we need to be able to like reverse the orientation as well. And that's easy because we can just swap any 2 of the vertices, and that changes the orientation of the triangle without doing anything else. But we'll need to know that we need to do that. So lots of things to keep in mind when you do a rasterizer, even a pretty basic one. But yeah, we'll just go ahead and get rid of a bunch of this here. The normal stuff was just to visualize it. And actually, there's some fun things about this. Now I've changed the code, but let's do git stash. In the beginning of this demo, it's kind of fun. There's a bunch of stuff where they have like this geometry that's just black. And if you look at some of this stuff, it looks like the normals are wrong because like there's a lot of green, which normally points up, but this clearly points down. And I think what they do for the black geometry is they just invert. They turn off culling and then they invert the model. And so it all ends up being black. Maybe that's what they're doing. I don't know. Just kind of a funny thing that I found. Anyway. Yeah, we want to get these window coordinates. That's what we want. And in particular, I want these in floats, in floating point coordinates. So we'll just do that. Also, the way that I'm laying this out in memory is kind of bad because I'm doing this arrays of structures approach, which is the easy one. So we have the position, and then I end up just overriding this for the transformed one, which we might change later. Viewport chords, and then I'll just do it like this. Maybe I promote this to a more proper, actually, you know what? I probably am going to want to promote this to a more proper vector class already. Because we're going to want to do like cross products and stuff on that. So let's just bite that bullet now. No, I'm not going to have shader support. We can just copy vec4, except vec4 is all vectorized already. And that's because I copied it from our demo engine. By the way, this is also not a great way to use SSE. In fact, if you really want to do stuff that's performant, this is not the way to do it. But we did this because it's small and simple code. And it's still better than doing it scalar in a lot of cases, but definitely not the best way you can vectorize stuff. Anyway, I'll just do it this way. Or you know what? I could even just do this. I could just take vec4 and then just use two components. I still want to make it a vec2. And then we're wasting two of the lanes. But I might just do that because who cares? Yeah, I'm doing that. I just had to do some due diligence before I decided that was okay. So we're going to make this vec2, and then we are going to get rid of Z and W, and then we're going to do that here too. This is stupid. But who cares? And then we'll do dot. So length and normalized work as long as dot works, and dot works if we just do one less horizontal product, or horizontal add, I mean. Yeah, that should work. And add div set one, whatever. Yeah, actually, I'm thinking this is a really bad idea now, because if those other components are, for example, 0 by default, and we do something like divide by it, that's probably bad. Yeah, this is not good. Actually, let's go ahead and do this anyway, though, so we get the same interface, and then we'll just implement it differently. This will be a fast way to do this. Also, I should do this. Why didn't I like this? Oh, yeah, because I didn't do mod vec2. I could get rid of this stuff, but I'm just going to keep it like this. And again, this stuff makes some sense. Dot is going to be really easy. We'll do... Okay. And then add, because it always produces a new one, so this makes it really easy. And then I did all the other ops kind of in terms of those, which was a good idea. So this is div. We don't have like sub. We might have to fill in some of these. Again, this is because of the way that I implemented this. We only had the stuff that we've used in the demo engine, so that's why there's a lot of stuff missing, and that's fine. Two curves, that'd be cool with like a visualization that updates as the demo's running. I guess that's the novel part there, rather than just a profiler. I think that'd be cool. I think most demos won't allocate much when it's running, but it would be a good debugging tool if you wanted to know if your demo was and how. Okay, yeah, we actually do have sub. I don't know why they're in this order. Probably because they're alphabetical. That's probably what it is. Good, and then we don't need this because we're not using SIMD. Okay, that makes me feel a bit better. Because then we're not going to get any nans or anything. Okay, now we wanted to go back and do some work. So what we wanted to do is have the viewport chords as a vec2. That's what this was about. So now I'm just being lazy. Oops, this would be... You know what I should also do? I'll go back here and put this here. Zero's fine. Yeah, because this is the only time that this actually gets added to, so that's fine there. And then when we do the transform, that's what we want to move. So I want to move this here. So right now it's just clipping before it calculates these window positions. Doesn't need to do that because it could always just calculate this anyway and then do the window check. So actually this is kind of a calculation we don't need in the first place. In fact, I'm going to remove that. And then we're just going to run this just to be sure about that, but I am pretty certain of that. Nothing bad happens if we don't do that. Everything's all white now because I changed that. But yeah, that's good. And then we can do this, where we don't need the NDC anymore. And we're going to calculate these down in end, I think is where I do that. Navigating this code isn't the best right now, but it doesn't need to be. NDC there. So here we have this, and this should actually become a bit easier because we can do let's viewport. In fact, I might just call this viewport. Do it this way, and then we can do viewport. And so viewport is NDC. Well, we can do this vec2 new NDC.x NDC.y. And then we can do viewport plus 1.0 times vec2 new self.viewport width SF32. Two plus use some parens here. I'm literally just flattening this expression down here. Oops. 5/2 plus viewport x. Oh yeah, that's the offsets, of course. So then this becomes vec2. So it's that. And let's go ahead and make this not quite so ugly. So we can do this out here too. I'll do it here and then let the compiler lift it. Position. Actually, we'll call this offset because we calculate the viewport with the size and the offset. I think we could call this. Yeah, I like that size. We'll do that. Then for dot position is NDC, and we can also do this where we do that. And then we'll just do this even. For dot viewport is this. Okay, it looks like I don't have add implemented for vec2, which is fine. Or at least not add where other is F32. That's all you need to do for that. Oh, yeah, I probably need to do this. Great. Love those traits. Whoa. Did not like that. Oh yeah, that's in the code above now. Vert dot. I think this will make it work. Oops. Don't know what I'm thinking there. There we go. I did this trait as usize, didn't I? That's probably fine. Just to verify that things still work, even though, again, this is not what we want to do yet. Indeed, things do still work. Another thing that I think I want to do is maybe get some kind of coloring for this triangle. Maybe we'll use like the first vertices or the first vertexes normal, but I'd rather, would be better if we had some kind of like hash of the sort of triangle index or something. Maybe I'll add a little RNG to the context or something that we'll use. But we'll work with this for now. But actually, we could bring back that other transform that we had for the normal. Which was this. Because this is still just rendering every vertex with a different color. But what we could do is this. So we get each one in vert 0, like this. That might be nice. Just because I want the different triangles to have different colors. It would be nice if they were more different between like adjacent triangles, but I think this will already be helpful. So already at least we can see a lot of disjoint, a lot of different colors here, which is what we're going to want. So now we want to calculate our bounding box. So instead of going through this, we actually are going to want to do this a couple times. We'll just comment that out for now. So let's do this. We will dot viewport. Oops. And I'm going to add a couple things here. Is there a trait for min and max in Rust? Oh, you have ORD that you can implement, and then you get min and max for free that way. That's actually not what we want for vectors. Because we want to do a component-wise one, not a total one on the whole struct, so that's actually not the mechanism we want to use. So then we'll do our own. Function min. And then we can do this will just be vec2 where x is just do compare min like this, and we'll do that same thing for y. I think I need to do that. In fact, I think I just imported min and max here, which I'll do here too. Like that, and then this will be min and oh yeah, ORD is not satisfied. That's what you mean too. Oh, does it have its own min and max? Okay, that's actually better than screw this. That's what we want to do. Rust F32 min. Is it on? Right, so you call it on the one. So we'll do self.x, whoops, here. Self.x.min, other.x. That's what we want. And we'll do the same for y. and save that. Looks like it's good. And then we'll do the same thing for max. And that makes the bounding box stuff really easy. Because then we'll do this, and we do for I in 1 for style length. Then we do BB. Make these mutable. I could also fold these, but this is just easy. Min is BB min dot min verts I dot viewport. Bounding box max is BB max dot max verts I dot viewport. There we have our bounding box. And what we can then do is translate these into integer coordinates. We'll do that next. So we'll do let BB min is BB min as GL int. I'm using these GL ones, which is probably dumb. I should probably use I32 actually. Let's do that. Let BB max is BB max as. Oh yeah, and of course these need to be we do this component wise. And I don't want to have integer vectors as well. We'll just extract them here, which I think is going to be fine. Okay, and then we could do clipping here. We could also do clipping here. So we take the bounding box with min and max like this, and then we could also do this. So I think we actually want to do BB min dot max. With the viewport X and Y. And should probably do this in integers, but that doesn't really matter. We'll have enough precision here, I think. We'll do min here. For the max here, which is plus self.viewport with of course. With the successor, I think it's that one that needs to be cast. Okay, and then when we translate this, we're gonna have bounding boxes that are also clipped to the sort of window coordinates, which is nice. And then we iterate, right? Also, these casts, we actually want to be careful because we kind of want to round these ones down and these ones up. Or the min ones down and the max ones up. Rust int round down. How do we do that? We have round, which of course still give us an F32. Trunk, seal, and floor. Let's just do that. We'll do this dot floor here and seal on the other one. Okay. And then we iterate. Y in BB min Y, BB max Y. For X in BB max X, BB min X, BB max X. And I think these are still, even though we did seal here, these should still be inclusive bounds. So I actually think we want to do that. Maybe not. Because then I think this actually needs to be -1 here. If these are to be inclusive. I think that's what we want. And then let's just try this. We are on our way. Oh, this is so slow. But it works. Oh, this is excellent. Oh, something just got real slow. Yeah, a lot of geometry there. This is not fast. Especially when you have a lot of polygons that cover a lot of area. This is so slow. Oh, that's great. This is so bad, you guys. But it's working. That's the important part. And in fact, if we... I don't really know where most of this time is going to go. I think the first thing I'm actually going to do is try to just make it a release build. Yeah, this is just a debug build right now. So let's just do a release build. In fact, all we need to do for that is that in my test script. Oh, and release. Hopefully that just fixes the speed issues. Yeah, it does look like voxels. That was my thought as well. Looks like Amiga demos. Or a lot of AGA demos I've seen, at least. From a certain Swedish group. Yeah, this is much faster. Which is great. In fact, this is real time. I just want to watch this for a second. This is fun. I love this, you guys. This is such a fun project. Yeah, so not all of it's smooth. And that's because it's a lot of fill rate, basically. And I'm wondering if it has to be. I wonder if a lot of that's culling as well, because like we're not doing frustum culling right now, which is a big one. So I think we're getting some crazy geometry that's like behind the camera and stuff right now. Yeah, exactly. This is the Bits remix. I actually did find some funny things in the code. I noticed that they were calling WGO get proc address with a function that didn't exist. And when I Googled what they were trying to request, I found a bunch of their demo code in Melwin's scene.org account. Which is actually kind of funny. lot of this too, there's gonna be a lot of stuff that's just like blended. And like any full screen polygon is just gonna be in front like this. But I do think a lot of these really large rectangles are stuff that's behind the camera, and we're probably gonna want to deal with that. Yeah, if you're curious about that misspelled function and stuff, I have it in one of the commit messages, and a link to that repository, at least I described where I found that other file. It's kind of funny. But I don't feel like digging it up right now. It's a bummer because a lot of this stuff is my favorite scenes, and we're just getting nothing because of this. It might also just be as simple as they're drawing the skybox last, which I guess is probably a performance optimization. Oh, that's funny, Daniel. Okay, so we have something that looks like some kind of rasterizer already. So that was easy. So let's go ahead and actually calculate the edge functions at all these positions, because we're cool like that. So let's do this. Let fx is x as f32, let fy y as f32, and we can even just do the edge function here. Edge where we have, we can also do this. UV is vec2 new x f32 y as f32. UV vec2 a vec2 b vec2, and just gonna return a float. And then we can say let p is a, let d is b minus a. It's gonna be a lot of calculations per pixel, and we don't care right now. So this will be uv.x minus p.x times d.y minus uv.y minus p.y times d.x. Okay, and then we'll do this exact same thing where we can do v0 equals verts 0 dot viewport, let v1 is verts 1 dot viewport, let v2 is verts 2 dot viewport, and then we can do e01 is edge uv v0 v1, and we'll do these for the other edges. 2 and 2 0. So much of graphics programming, it's just a lot of typing. At least programming at this level. At least the way I've always done it, which I've been doing this kind of crap for too many years. Anyway, then we'll just do the inside. So we'll do let inside is this same thing I had in the shader. And then this is if inside we do this. And this might work. Oh, what up? That's so cool. Oh, that makes me happy. And crazy stuff going on here. Again, probably geometry that's behind the camera. But see, this is why this is totally the right approach, because we can kind of just make a lot of progress pretty fast. And even if we end up with something unusably slow right now, it's at least working. I just like watching it. I want to see how far it gets and what we can see. This is awesome. That cube again. Don't know why. Having so much fun with this approach, you guys. And again, when we resize this window, the content gets resized. It's so funny. One thing I think I want to do here is, by the way, are you guys seeing that my screen like goes black whenever I close that window? No idea what's happening there. That's fun. I think what I want to do is, I think I want to skip this, like, because I don't want to actually do frustum culling. Right now, at least. So what I think I'm going to do is do a really crappy version where if any of the vertices are outside of the frustum, we're not going to draw the polygon. At least I want to do a version of that where if any of the vertices are behind the camera, I think that's actually the one I want. Yeah, so we could actually just do the z coordinates. So we could do if or for vert in verts dot iter if vert dot ndc dot z, or did I do ndc that way? I think I did ndc as the, so in ndc it should just be if this is less than -1 or vert.ndc.z is greater than 1, then we'll just return. What? Oh, did I not save those? Oh yeah, the position is that now, which is fine. Good enough. This will also reject on the other side of the frustum, but this way I don't have to worry about signs and which is which. And I'm not sure if this is more well behaved yet. I'm guessing it is, but, and of course this is also too conservative. And eventually we'll want to do that properly, but we'll do it properly by actually doing clipping. So I think this is actually exactly what we wanted for now, at least. Yeah, this is much better. I'm so pleased with this. I'm not getting those references, MSIS. This geometry is so messy. What is even happening? Also, of course, we're not doing like Z buffering or anything. I actually have space allocated for Z buffer, and doing that check wouldn't be terribly difficult as long as we actually got the function. And for that, we need to calculate the deltas. Maybe I could do that quick. I'm also like not using any of the texture coordinates or the normals properly. As you hear, we can see stuff getting clipped. But I think I'll actually go instead because it's a little bit late. But I'm thrilled with this progress. This is actually a little bit farther than I wanted to get today, so that's great. Even after I talk so long about this. This is kind of interesting because there's a whole model that's just missing here. That's probably because this background thing is probably drawn after it. But who knows? Test that. I should test this with Liquid Wind. I should do that really quick right now, because worst case is what I expect, and then it uses some feature that this demo didn't, which may or may not be the case. I mean, it's presumably the same or similar engine, so it might work. Same people, similar time, so it's not unheard of that this might work. We'll give it a shot. Oh, my virus scanner was not happy about that. Open. Okay. So just to be sure, I'm going to run it on its own first. Oh, it went full screen. That might be an issue. It went full screen, which is kind of annoying. I'm still going to try it, though. So let's just move it into that project directory. Actually, we don't even need to do that, because what we can do is just do the other way. All we need to do is copy my OpenGL32 and run it. And if it doesn't work, then screw it. I'm not gonna fight with it today, but maybe later. Yeah, 400K for my OpenGL32. It does all that. So if I run this, am I in a compressed folder? What? That should not have been the case. I double clicked the wrong thing. Yes, I did. That's fine. Yeah, geo copy text sub image 2D cannot be found. So it's probably doing some feedback or something. So this is a function I don't support. So yeah, it didn't work. That's fine. Definitely worth a shot. The other thing also with this mosaic demo, we might have the culling backwards. I don't think we do, but we might. Yeah, I just want to watch it one more time, and then I think I'm going to head out. Just because I think this is cool. Try and center it. Now we won't watch the whole thing. Okay, this is great progress. Yeah, another thing we're definitely going to want to do too is once I have blending, then we want to be more strict about accepting or rejecting pixels, or essentially determining whether or not a pixel is inside the triangle. We need to implement like a top left rule or something. But again, that's for later. You know what? I actually want to do one more thing here. And then I'll go. And specifically what I'm thinking I want to do is average the pixels instead of setting it here. And that way, we can at least have some semblance of all the geometry that's visible, even though it'll be in the wrong order and all this other crap. I think that'll be a good idea. So we can do, let's, shift right 16 and this. Like to be explicit with these shifts, even though this one's a no up. And then what I can do, I think this will be a U32, so we'll do this. Just to make that match, and then we can do okay. Oops. Whoops. Then we'll do this. We'll do color alpha, shift left 24, or color red, shift left 16, or color blue, shift left, no, green, shift left 8, or color blue. And all of that needs to be U32. This way we'll at least see all the geometry. You can see also there, when there's the full screen quads, there's a couple pixels where there's overdraw. I don't know if you guys can actually see it on the stream, but that's why we need to be more strict about what's inside or outside of a polygon. But now we see, like when there's overdraw, we see all the geometry, which is kind of nice. At least as a debug view, that makes this a bit more useful. So here we can see that there's actually multiple of these sort of curved surfaces drawn on top of each other, which was really obvious when we were just displaying the vertices, but Now we can see that a bit as well here. Also, averaging the newest ones definitely makes the ones drawn last take a lot of precedence, but that's okay. We have a lot of overdraw, we'll just exponentially lose the background stuff. Again, totally fine for a debug view. See, this is a lot cooler where you see how much geometry there is. Oh, I'm so happy with this. I'm gonna finish the demo and then commit this, and then I'll head out. Yeah, here also you can see the different layers of the background geometry too, where there's like this cliff thing and the sky sphere, which is nice. No worries, load to cable. This is way before the hardware for this part at least. So this is just a software model, and the hardware in general is very work in progress. I have a working CPU and some other stuff, but none of this 3D rasterization stuff, which is why we're doing this model. Okay, there's also a lot more geometry visible. Yeah, now you can see the kind of person in the scene. Not very brightly, or not very well, because it must be one of the first things drawn. So it's probably a lot of other things drawing over it, but still cool to see. Yeah, I'm curious to see that too. I don't know. I don't know exactly what it's gonna be. I still think it's funny that there's this stupid cube here. No idea why. Cool. Okay, I'll go ahead and commit this. Not much more to say than that, because otherwise it's just listing to-dos. Cool. All right. Thanks, guys, for hanging out, and I'll see you next time.